Welcome to our comprehensive guide on Java programming. In this video, we'll explore the foundational concepts of Java, starting from the architecture of the Java Virtual Machine or JVM and moving through essential object-oriented programming principles. Whether you're a beginner or brushing up on your skills, this journey will help you understand how Java works under the hood and how to use its core features effectively. Let's dive in and start with the basics of the JVM and why it's so important for Java developers. Java Virtual Machine or JVM is at the heart of Java's platform independence. It's an abstract machine that provides a runtime environment for executing Java bytecode. Think of the JVM as a virtual computer that runs your Java programs, regardless of the underlying hardware or operating system. This means you can write Java code once and run it anywhere. The JVM specification outlines how it should work, but different companies like Oracle can implement it in their own way. When you run a Java program, an instance of the JVM is created to execute your code. JVM does much more than just run code. It loads your compiled Java classes, verifies that the code is safe and valid, and then executes it. It also provides the runtime environment needed for your program to function. The JVM defines memory areas, class file formats, register sets, and manages the garbage collected heap. It even handles fatal error reporting, ensuring your program runs smoothly or provides useful feedback if something goes wrong. This robust environment is what makes Java reliable and secure for developers. Let's break down the JVM's memory structure. The subsystem loads class files when you run a Java program. The class or method area stores per class structures, including runtime constant pools and method data. The heap is where objects are allocated at runtime. The stack holds frames for method calls, local variables, and partial results. The program counter register keeps track of which instruction is being executed. The native method stack contains native methods used by your application. Finally, the execution engine interprets and compiles, making your program run efficiently. Execution engine is a critical part of the JVM. It acts like a virtual processor interpreting and executing instructions. It also includes the just-in-time or JIT compiler, which translates into native machine code for faster execution. Another important component is the Java Native Interface or JNI. JNI allows Java to interact with applications written in other languages like C or C++. This is how Java can send output to the console or interact with operating system libraries, making it a versatile language for many applications. Now let's shift gears to Java constructors. In Java, a constructor is a special block of code that looks like a method but is called automatically when you create an instance of a class. Constructors are used to initialize objects and allocate memory for them. Every time you use the new keyword to create an object, at least one constructor is called. Constructors help set up your objects with initial values and ensure they're ready to use right after creation. There are a few important rules to remember when creating constructors in Java. First, the constructor's name must match the class name exactly. Second, constructors do not have a return type, not even void. Also, a Java constructor cannot be abstract, static, final, or synchronized. These rules ensure that constructors are used only for initializing objects and not for other purposes. Following these guidelines helps keep your code clear and consistent. Default constructor in Java is a constructor that doesn't take any parameters. If you don't define any constructor in your class, Java automatically provides a default one. This constructor is useful for creating objects with default values. For example, when you create a new object of a class without passing any arguments, the default constructor is called, initializing the object with standard settings. Let's look at a simple example of a default constructor. Imagine a class called bike1. Inside this class there's a constructor with no parameters. When you create a new bike1 object, the constructor prints a message saying, "Bike is created." This demonstrates how the default constructor is automatically called when you create an object, ensuring it's properly initialized. Parameterized constructor is a constructor that takes one or more parameters. This allows you to create objects with specific initial values. For example, if you have a rectangle class, you can use a parameterized constructor to set the length and breadth when creating a new rectangle object. This gives you flexibility to create objects with different properties, rather than relying on default values. Parameterized constructors are especially useful when you want to create multiple objects with different values. For instance, you might want to create several rectangle objects, each with its own length and breadth. By passing these values as arguments to the constructor, you ensure each object is initialized exactly as you need. This approach is more efficient and makes your code easier to manage. See an example of a parameterized constructor in action. In the rectangle class, the constructor takes two parameters, length and breadth. When you create a new rectangle object and pass values for these parameters, the constructor sets the object's properties accordingly. You can then call a method like getArea to calculate and display the area of the rectangle, showing how parameterized constructors make your objects more dynamic. Java, constructors can be overloaded just like methods. Constructor overloading means having more than one constructor in a class, each with a different parameter list. This allows you to create objects in multiple ways depending on the information you have. The compiler differentiates between constructors based on the number and types of parameters, making your classes more flexible and adaptable. Inheritance is a core concept in Java's object-oriented programming. It allows one class to acquire the properties and behaviors of another class, known as the parent or superclass. This means you can create new classes based on existing ones, reusing code and adding new features as needed. Inheritance helps organize your code, promotes reusability, and supports the ISA relationship, also called the parent-child relationship. Let's clarify some important terms in inheritance. A class is a blueprint for creating objects with common properties. A subclass, also known as a child or derived class, inherits from another class. The superclass or parent class is the class being inherited from. In Java, you use the extends keyword to indicate that a class derives from another. This structure makes it easy to build complex systems from simpler building blocks. Java supports several types of inheritance. The most common are single inheritance, where one class inherits from another, and multi-level inheritance, where a chain of classes inherit from each other. Multiple and hybrid inheritance are supported through interfaces. Understanding these types helps you design more efficient and organized code structures. In single inheritance, a class inherits from just one parent class. For example, consider an animal class with a method eat and a dog class that extends animal and adds a bark method. When you create a dog object, it can both bark and eat, demonstrating how the child class inherits the parent's behavior while adding its own unique features. Multi-level inheritance involves a chain of classes, each inheriting from the previous one. For instance, you might have an animal class, a dog class that extends animal, and a baby dog class that extends dog. The baby dog class inherits features from both dog and animal, allowing it to use methods like eat, bark, and weep. This structure enables you to build more complex hierarchies in your programs. Method overloading is a feature in Java that allows a class to have multiple methods with the same name but different parameters. This is useful when you want to perform similar operations with different types or numbers of inputs. Overloading improves the readability of your code and makes it easier to manage related methods under a single name. There are two main ways to overload methods in Java: by changing the number of arguments or by changing the data types of the arguments. For example, you might have an add method that takes 2 integers and another add method that takes 3 integers or 2 doubles. The compiler determines which method to call based on the arguments you provide. Let's look at an example of method overloading. Suppose you have an adder class with 2 add methods, one takes 2 integers and the other takes 3. When you call add with 2 arguments, it adds them together. When you call it with 3, it sums all 3. You can also overload methods by using different data types such as integers and doubles, giving you even more flexibility. Super keyword in Java is used to refer to superclass objects. It helps you access methods and variables from the parent class, especially when there's a name conflict between parent and child classes. The super keyword can also be used to call the parent class constructor, making it easier to manage inheritance and avoid confusion in your code. You can use the super keyword to access instance variables from the parent class when the child class has a variable with the same name. For example, if both animal and dog classes have a color variable, using supercolor in the dog class will access the color from animal, while just color refers to dog's own variable. This helps avoid ambiguity and makes your code clearer. Super keyword can also be used to call methods from the parent class, especially when the child class overrides a method with the same name. This is useful when you want to extend or modify the behavior of the parent method but still need to use its original functionality. Simply use super method name to invoke the parent's version. You can also use the super keyword to call the parent class constructor from the child class constructor. This is especially important when the parent class needs to be initialized before the child class can set up its own properties. By calling super, you ensure the parent's constructor runs first, maintaining the correct initialization order. Final keyword in Java is used to restrict how variables, methods, and classes can be used. When you declare a variable as final, its value cannot be changed. If you declare a method as final, it cannot be overridden by subclasses. And if you declare a class as final, it cannot be extended. This helps enforce certain rules and prevent unwanted changes in your code. Final variable in Java is a constant. Once you assign it a value, you can't change it. For example, if you declare final int speedlimit equals 90, the value of speedlimit will always be 90 throughout your program. This is useful for defining constants that should never be modified, making your code more predictable and secure. When you declare a method as final, it cannot be overridden by subclasses. This is useful when you want to prevent subclasses from changing the behavior of certain methods. For example, if you have a method that handles critical operations, making it final ensures that its logic remains unchanged in all subclasses. Final class in Java cannot be extended by any other class. This is useful when you want to prevent inheritance for security or design reasons. For example, you might create a final class for sensitive operations or to lock down the implementation of certain features, ensuring that no other class can modify or extend its behavior. This keyword in Java is a reference variable that refers to the current object. It's used in many situations, such as resolving ambiguity between instance variables and parameters, invoking current class methods or constructors, and passing the current object as an argument. This keyword helps make your code more readable and avoids confusion when working with object properties. This keyword is often used to refer to the current class's instance variables, especially when there's a naming conflict with method parameters. For example, in a student class, you might have parameters named rolno, name, and fee. By using this, rolno equals rolno, you make it clear that you're assigning the parameter value to the instance variable, resolving any ambiguity. You can also use the this keyword to invoke methods of the current class. In most cases, the compiler automatically adds this when calling methods, but you can use it explicitly for clarity. This is helpful when you want to make it clear that you're calling a method on the current object, especially in complex classes. This constructor call is used to invoke another constructor in the same class. This is known as constructor chaining and helps you reuse code by calling the default constructor from a parameterized one or vice versa. It ensures that all constructors properly initialize the object, reducing code duplication and potential errors. You can pass this keyword as an argument to methods. This is especially useful in event handling or when you need to pass the current object to another class or method. By passing this, you allow other parts of your program to access and interact with the current object, enabling more flexible and modular code. This keyword can also be passed as an argument in constructor calls. This is useful when you want to use the current object in another class, such as when setting up relationships between objects. By passing this, you make it easy for other classes to reference and interact with the current instance. You can return this keyword from a method, allowing method chaining or fluent interfaces. In this pattern, methods return the current object, enabling you to call multiple methods in a single statement. This approach makes your code more concise and expressive, especially when configuring objects or building complex operations. Interface in Java is a blueprint for a class. It defines a set of abstract methods and static constants but no method bodies. Interfaces are used to achieve abstraction and support multiple inheritance in Java. By implementing interfaces, classes can promise to provide specific behaviors, making your code more modular and flexible. There are several reasons to use interfaces in Java. First, they help achieve abstraction by defining what a class should do without specifying how. Second, interfaces enable multiple inheritance, allowing a class to implement multiple interfaces. Third, interfaces promote loose coupling, making your code easier to maintain and extend. To declare an interface in Java, use the interface keyword. All methods in an interface are abstract by default, meaning they have no body. Fields in an interface are public, static, and final by default. Any class that implements an interface must provide concrete implementations for all its methods, ensuring the required behavior is present. When a class implements an interface, it must provide concrete implementations for all the methods declared in the interface. This ensures that the class fulfills the contract defined by the interface. Implementing interfaces allows you to define common behaviors across different classes, making your code more consistent and easier to maintain. Let's look at a simple example. Suppose you have an interface called printable with a method print. A class named A6 implements printable and provides the print method's body. When you create an object of A6 and call print, it displays a message. This demonstrates how interfaces define required behaviors and how classes implement them. Java does not support multiple inheritance through classes, but interfaces provide a way to achieve it. A class can implement multiple interfaces, inheriting behaviors from all of them. This allows you to design flexible and powerful systems where classes can take on multiple roles, each defined by a different interface. Interfaces are a key tool for achieving abstraction in Java. By defining what methods a class must implement, interfaces separate the what from the how. This allows you to focus on designing the structure of your program while leaving the details of implementation to individual classes. Abstraction makes your code more modular and easier to understand. Using interfaces helps achieve loose coupling in your code. When classes interact through interfaces rather than concrete implementations, it's easier to change or replace parts of your system without affecting the rest. This makes your codebase more flexible, maintainable, and adaptable to future changes. We've covered a lot of ground in this video, from the architecture of the JVM to key object-oriented concepts like constructors, inheritance, method overloading, and interfaces. Understanding these core ideas is essential for mastering Java and building robust, maintainable applications. Keep practicing these concepts, experiment with your own code, and you'll become a confident Java developer in no time. Thanks for watching and stay tuned for more in-depth Java tutorials.